Paula, and this is my Lab 6 for Physics 2212. So, introduction. So, the main purpose of this lab was to basically to investigate magnetic induction and currents by analyzing how falling bar magnets interact with an aluminum tube. And we're just basically comparing the observations to a computational model. So, from our code, we had the magnet fell in 2.021 seconds through the tube, and in real life 1.5 seconds. So the introduction to the fundamental physical principles. So we did Savart's law, which calculates the magnetic field generated by constant electric field, and the formula is shown right there. Faraday's law, when the magnetic flux changes over time, the electromotive force is produced, and here's the formula for that. And Newton's third law, which everyone should know, forces have equal and opposite reactions. So this is our experiment model. So the initial conditions are the bar magnet, of course, the phone, which we had we took the video of the magnet falling through. The system is also the bar magnet and the aluminum tube, and the surroundings is everything else. So data collection. So for our magnet, we got the mass is 0.035 kilograms. The mu is 3.458 times m squared. The tube has a length of 0.5 meters. The width is 0.008 meters. Inner radius is 0.02 meters. Outer radius is 0.028 meters. And the average time was 1.5 seconds, as shown back here. Okay, so into our computational model, starting from the top. So this is just the first part. We're just doing the geometry of the tube. We're putting the length, the width, the inner radius, and the radius, which is the outer. We're just putting all that together. And this is the next part, which we weren't supposed to edit. And then over here, I'll take you down the code a bit more. This is the mass of the magnet. We're just putting in the properties of the magnet. And here's the mu of the magnet, which we got from Lab 4. And here's us visualizing the bar magnet, how it's going to look. I will show you how that looks in a couple more slides. Over here, we show the calculations of the magnetic flux. So I showed you the formula. This is basically it in code. Same thing over here with the dipoles. This is the magnetic field for a dipole. And then over here, we are calculating the magnetic force of the magnet, which we know how to do already based off of our test that we just took. And that's basically it. It's just straightforward code. Straightforward, nothing really going on. So here's our computational results. As you can see, our time in the tube was 2.02 seconds. Here's our graph. Over here, we have what the bar magnet looks like going down. It goes down in 2.021 seconds. Which is nice. So similarities and differences between our computational and experimental. Of course, the big was the seconds, the time. So experiment is 2.021 seconds. Computational time is 1.5 seconds. So assumptions are that the bar magnet acts as a magnetic dipole, to use Biot's law, negligible air resistance, and only forces involved are magnetic and gravitational. So what went wrong? Some errors may include like friction with the magnet in the tube, with the magnet touching the tube, not having steady hands when holding the tube, which kind of piggybacks off of the friction, and the rough calculation of the average time of the videos. It may have not been super precise, but we worked with what we had. So the questions are, what if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? So the answer to this was that the induced current in aluminum will be much greater, which will cause the magnet to never fall, basically stopping the magnet. So what if holes or slots were cut into the tube? How would this affect the ring's current in your model? So an induced current in aluminum tube would be less, since the holes would disrupt the current and magnet would fall much quicker. Basically, the magnetic field is not able to attain inside the tube. So the mu and everything else is just passing through. The flux just releases. And that'll be it. Thank you.